Hi. A blank copy of these notes is on Learning Studio. If you like to take notes, you're welcome to print those out and follow along. We have 2 days to spend on this topic, triple integrals in cylindrical and spherical coordinates. So today will be a video lecture, and then on Monday we'll pick back up again and finish the topic. So remember last time we talked about cylindrical and spherical coordinates as two other ways, other than our rectangular XYZ coordinates, of describing points in three-dimensional space. And so now we want to work out calculations like finding volumes, finding masses, and so on of three-dimensional objects. And whenever you decide you're going to use a new coordinate system to do integral calculations, one of the main things is to work out what is this dV. If I have a little chunk of solid, what is its volume in terms of the three variables that we're using? So in cylindrical coordinates, a chunk looks like this. There's a little bit of dr along here, and a little bit of dz along here, and then theta is this angle in here. So from trigonometry, this is r d theta in here. And this solid is approximately a rectangular solid, and so it's the product of the three dimensions. That's not real rigorous. How do I know that that approximation is good enough? So in homework, you actually, I hope, worked out this calculation, where you take the 3×3 determinant of the Jacobian matrix. And because these two entries are 0, and this entry is 1, it's actually a reasonably simple calculation to show that dV is r dr d theta dz. Reminds you of polar coordinates, where the area element was r dr d theta. Spherical coordinates, a little more complicated, considerably more complicated actually. So a geometrical picture would look like this, and a little chunk of dV is shaped like this. We could use some trig if we wanted and find out what the volume element of that thing, the volume of that element is. Or you could do a purely mechanical calculation, a bit complicated, but not too bad, to calculate the Jacobian. So again, it's a 3×3. You take these equations, work out all of these partial derivatives, and you can show that it's rho squared sine phi, and then d rho d phi d theta. So you don't want to work these out each time. These are things to be memorized, and it'll probably happen automatically as you do the homework calculations. First question. Here's a solid. It's bounded below by the graph of z equals 0. That's this plane, of course, the xy plane. Laterally, or on the side, by this graph. Notice that the z variable is missing, so this is a cylinder. In fact, it's a circular cylinder. It's just that the y-1 makes it offset from the origin. The origin is in here, and then the cylinder is scooted along the y-axis. And above by the graph z equals x squared plus y squared. So that's a piece of a paraboloid, and it looks like this. So bounded by these three surfaces is this solid in here. You can't see inside it, but that's the solid that we're talking about. And I want to find the mass of this solid, so I need to know its density. And in fact, we're told that its density is proportional to the distance from the z-axis. So the z-axis is coming along through here, and actually it's going to be like in here. And so then the farther away from the z-axis you get, the denser the object gets. So here it's fluffy as you move out away from the axis, getting more and more dense. We want to know the mass of the solid. It's going to depend on this constant k, so the problem says it's okay to use k in your answer. All right, before we choose our coordinate system, let's write down the density. It's proportional to the distance from the z-axis. So is proportional to means equals k times, and then distance from the z-axis, that has nothing to do with the with the z variable itself. It's involving the xy variable, and if you think about it a little bit, it's square root of x squared plus y squared. So there is the density expressed in rectangular coordinates. And here is the geometry of the problem, and now we need to choose between, are we going to set up this integral in rectangular coordinates, or cylindrical coordinates, or spherical coordinates? This is a problem, I think, where the choice is overwhelming and hopefully fairly intuitive and obvious as well. First of all, this density function, it's written in rectangular coordinates, but it's a bit clunky, square root of the sum of the squares and so on. X squared plus y squared square root, you recognize from your work with polar and cylindrical coordinates, is just the variable r. So the density is particularly simple to write in the r variable, which is one of the variables of cylindrical coordinates. So yahoo for cylindrical coordinates. Now if we look at the geometry itself, I also see a cylinder there. It's true that it's offset from the z-axis, which will mess things up a little bit, but I still see cylinders happening, and here's a x squared plus y squared that seems related to cylindrical coordinates as well. So for a number of reasons, geometry as well as density function indicate that cylindrical coordinates would be best. So let's see what we can do. I think I should next look at the projection of the region onto one of the coordinate planes. So I could project down onto the xy plane or try to project over onto the xz plane and so on. The symmetry of the problem suggests that we project downward onto the xy plane. And so what does it look like there? Notice that I'm talking about the xy plane, even though I've chosen cylindrical variables. You can think in whatever system that is easiest at the particular moment. What we see is a circle, and it is symmetric with respect to the y-axis, but it is along the y-axis. In other words, there's a circle that looks like this. Its radius is 1, and its center is at 0, 1. So that can be obtained from this equation. And now I would like to know the equation of this in whatever variables that I've chosen to use, in this case in cylindrical coordinates. So if I just start from the equation as given, which is like this, let's take this and move to r theta z variables as needed. So I think I see an x squared plus y squared in here. Let's go ahead and expand the binomial. And of course the ones cancel. There's an x squared plus y squared, which is r squared, and minus 2 times y, and y is r sine theta. If we factor out an r, we get here, r equals 0 is just the origin. That's not interesting, but this other factor being equal to 0 is significant. R equals 2 sine theta is actually the equation of this thing in cylindrical coordinates. And now I think we're ready to set up the integral. So this is a mass calculation for the variable m. It's going to be a volume calculation, so triple integral. And then if I'm trying to calculate mass, What I integrate is the density function, which we got kr for that, remember? And then here goes dv, and so I'll write it, but I actually want to put something in, and here is when I'm making my choice for the order of integration. Is it going to be dz, d theta, d r, or dr, d theta, dz, and so on? In this case, it probably doesn't matter so much. Let's put down r, dr, let's go r dz, dr, d theta. I say it doesn't matter. It matters a little bit. Let's go with the z variable on the inside because that gives me the most flexibility in choosing limits of integration. Now I can choose things that involve both the r variable and the z variable in the limits of integration. I said that wrong. I can choose things that involve both the r variable and the theta variable in limits of integration for the z variable since z is inside. Okay, where does z go? If I am inside this region and I look down, I see the floor, which is z equals 0, and I look up and see the ceiling, which is this flying sheet kind of paraboloid, and the equation of that is z equals x squared plus y squared, or in other words, z equals r squared. Regarding the r variable, so now I talk about how far do I move from the origin in the xy plane until I enter the region? 0. It immediately happens as I leave the pole. And how far out do I go? Well, r equals 2 sine theta. And how about the theta variable itself? In order to get this circle and nothing else, theta starts at 0 radians right along the positive x-axis and sweeps through the angle pi until it's tangential. The curve is tangential to the negative x-axis, so 0 to pi. So actually I commented earlier it doesn't matter. In this case I think it does matter. And again, the reason for choosing this particular order of variables is to give yourself flexibility when you're writing down these limits of integration. Okay, this is now an easy integral to do, and you can show that it is 512k divided by 75. So we were allowed to use k in our answer. Remember, find the mass of the solid in terms of k. All right, this is an easy integral to do by hand. Better yet, to use Maple. And so here is sample Maple syntax. You only need to type the content on the right-hand side. That's what actually cranks out the answer. If you put capital I's on the ints, that causes Maple to print out what the command actually is doing, so you can check for correct entry. Or in Maple you can use the menus, and there is a triple integral option, and then you can mouse click and fill in these things as well. That's probably just as easy or easier. Let's do a couple of other examples involving food. So find the volume of the ice cream cone lying above the cone and below this sphere. Okay, no picture this time. Let's see if we can draw one ourselves. So here is x, y, z. And regarding the cone, z equals square root of x squared plus y squared. So this is also known as z squared equals x squared plus y squared. And if you think about it or look back at your quadric surfaces, you can identify the fact that this is indeed a cone. like this, and I won't draw the top quite yet. Actually, there is no top to the cone, but if we were drawing it, I would put a circle here on the top to visually show what's going on. And the sphere, x squared plus y squared plus z squared equals z. So careful here, this is not a constant, and so I shouldn't be immediately jump to the conclusion that it is a sphere. It is, but to see that, you need to complete the square. So x squared plus y squared plus z squared. Now bring the z over, and then add something to complete the square. Half of the linear coefficient is negative a half. Square that and get a fourth. So adding a fourth to both sides lets me write this as x squared plus y squared plus z minus 1/2 quantity squared equals 1/2 squared. Okay, so here's the form that tells me, yes, indeed, it is a sphere. And the center is at 0, 0, 1/2, and the radius is a half. So if I come over here to height 1/2, that becomes the center of a sphere. And if I graph this, then what's happening is there is indeed a half of a sphere that comes up here, and then like this. Okay, now let's look at the question again. The region lies above the cone and below the sphere. So if you think of a ice cream cone, it is really the volume of the ice cream itself. You can pack ice cream down in the cone itself, and then it's mounted up on the top in a hemisphere. And if this came on up, we could find that this is the point 0, 0, 1, where the ice cream reaches height 1. Okay, need to make a choice about coordinate systems now. So there is a hemisphere that has lots of squares of variables. That might suggest spherical coordinates. It's the center of the sphere is not at the origin for the simplest form, but at least it is a sphere. And then here's a cone, and if you look back to our examples from last time, cones are reasonably okay to express in either cylindrical or spherical coordinates, better in spherical coordinates probably, and that's what we have. So for geometrical reasons, this time only geometrical reasons, choose spherical coordinates. So I need the equations of the corresponding surfaces here. Regarding the sphere itself, what we have is, let's come all the way back to this equation. On the left-hand side, x squared plus y squared plus z squared is the spherical variable rho squared. On the right-hand side is z. And if you look up your coordinate, change of coordinate formulas, this is rho cosine of phi. So I can factor a rho out of both sides, and I'll go ahead and cancel it. Rho equals 0 is just the origin again, not interesting. So rho equals cosine of phi is the spherical coordinate version of this hemisphere. Regarding the cone, z equals square root of x squared plus y squared. So this will take a little working out. I'm taking this equation and getting rho cosine phi equals square root of, and now in spherical coordinates, unfortunately the x and y variables are a bit complicated. Rho sine phi cosine theta is x, and rho sine phi sine theta is y. So like this. So it's a bit messy, but then nice things start to happen. The rho sine phi can be factored out of both terms, and then I have a cosine squared theta plus sine squared theta. So that's 1, and I get square root of rho squared sine squared phi. And I want to take this square root, and I can just take the expression rho sine phi, because rho is a positive number, and phi, sine phi is also positive. Remember, phi is the angle from the positive z-axis, so it goes between 0 and pi, and therefore its sign is always a non-negative number. So now I have rho cosine phi equals rho sine phi. I'll just write that down again. Rho cos phi equals rho sine phi. Again, phi equals 0 is not interesting, and so we get cosine phi equals sine phi. I keep churning on it a little bit. Divide both sides by cosine phi, and we get 1 equals sine phi over cosine phi. That's tangent of phi. Okay, so the equation has simplified considerably. Tangent of phi equals 1. We are looking for now an angle from the polar axis, or z-axis I should say, whose tangent is 1, and that happens at angle pi over 4. That tells us that phi is the angle pi over 4, the angle of the cone. All right, ready to set up the integral. It's a volume, so triple integral. Our volume element, and the integrand, by the way, can be 1 since we're doing purely a volume calculation. So dv. And now we have a choice of order of integration. I know there's going to be a rho squared sine phi, and then in any order, d rho and d phi and d theta. So first of all, nothing about the problem indicates anything other than perfect symmetry in the theta variable. So I think I'll put that last because it doesn't interact with the other things. Regarding rho and phi, it seems pretty clear that phi is going between phi equals 0, which is straight up, and phi equals pi over 4, which we went to some difficulty to work out. And regarding the rho variable, it's, if I think now about moving out from the origin, notice that I immediately enter the ice cream as I leave the origin, and I go until I hit this hemisphere for my outer limit of integration or upper limit of integration on the rho variable. So here's what the expression is, and therefore I want to use variable phi in the limits of integration for rho. So d rho, d phi, d theta is the best choice probably for the order of integration. Then phi does go from 0, rho does go from 0 to cosine phi. Phi goes from 0 to pi over 4, and theta goes from 0 to 2 pi. And if you have Maple calculate this, it is pi over 8. One more example, also involving food, donuts in this case. And by the way, I did bring donuts to class. Here they are. And now let's do a calculation involving them. So here is a donut, which in mathematics is called a torus. To specify a torus, you need to give 2 radii. One is the radius of the kind of the ring, how big is the ring, and then the other is the radius of the yeast part itself, how big is the cross-section. So the orbital and the tubular radius, they're called. Suppose I have a torus with orbital and tubular radius, both 1.5, and the z-axis is the axis of symmetry. So then I have a picture like this, where the z-axis is going down through the center of symmetry of the donut, and then I can put an x and a y here to think about it. So put the origin right at the center of symmetry of this problem. Seems to make sense. But notice that the orbital and tubular radius are the same, and so if I think about what that means, the picture in this case actually looks like this in cross-section. And this is the z-axis, and then this either is the x or the y-axis, depending on just which way I slice to help set things up here. Okay, the density is proportional to the distance from the z-axis with constant of proportionality k. So we saw that before. You know that density equals k square root of x squared plus y squared. I know that that is a particularly simple expression in cylindrical coordinates, so that might be an option. Or spherical coordinates, I think, is the other contender. Rectangular coordinates seems to be the worst in this problem. There are lots of circles going on here that the other coordinate systems take advantage of. Let's look at this cross-section. As I leave the origin, I immediately enter the donut and would go out to where I hit this boundary. So the decision is I want to express this boundary either in terms of cylindrical or spherical coordinates. So what I notice is that this is a circle. And remember, in polar coordinates, the equation of a circle is fairly simple. I think this integral could be set up and done in either cylindrical or spherical coordinates, but let me show you something here. If we think about this being the variable phi, which it is, it's the angle from the positive z-axis, then this sort of reminds me of polar coordinates. I'm talking about the distance from the origin and an angle from an axis like this, only it's not polar coordinates in the xy plane, it's polar coordinates in the yz plane here. If I remember results from polar coordinates, though, the equation of this circle is rho equals 3 sine phi, where rho is this distance from the origin. And this could be converted to cylindrical coordinates and then continue from there in cylindrical, but it seems most naturally here to be set up in spherical coordinates. And so let's try to do the integral in spherical coordinates. If I work on that a little bit, then this is kr, kind of going to cylindrical coordinates, but then continuing on to spherical, it's not bad to express this. R is rho sine phi. So the expression for the donut boundary as well as the density expression is fairly simple in spherical coordinates. Seems like it should work. So calculating a mass here, m equals triple integral. Here I put the density function, k rho sine phi. Then I have the volume element, so that's going to be another rho squared sine phi. and then the three differentials, d rho, d phi, d theta, in the order that I prefer. Again, the order of the theta variable is not so important. Theta is the angle around the z-axis. I'm going a full 0 to 2 pi rotation, and there's perfect symmetry there. So I'll just put theta last out of the way here. And regarding the other two variables, as in the ice cream problem, if I move out and determine my limits of integration in rho, I see that it's very convenient to use the variable phi to do that. So put d rho first, and then d phi, and finally d theta. Then phi goes from 0 to 3 sine phi. Rho goes from 0 to 3 sine phi. Phi, so the circle is tangent to the positive z-axis, and so phi starts at 0, and it works its way around until it's tangent to the negative z-axis. By that time, phi has run through pi. Theta is a full 0 to 2 pi revolution around the z-axis. So this integral actually could be calculated by hand. There's no need to do that. Maple will tell us this is 405 pi squared k over 32. So all that to find out how much your donut weighs, and then you could find out how many calories it has, and probably shouldn't be eating it anyway. All right, we'll pick up again on Monday. Thank you.